morning students, welcome to Lakshya Academy YouTube channel. Up to now we've completed first part of the semiconductor devices chapter. So in that part we have to complete some problems. Today we discuss that formula list. In an intrinsic semiconductor, Ne equal to Nh equal to Ni, Ne electron density, Nh hole density, Ni intrinsic carrier concentration. For n-type semiconductors, Ne nearly equal to Nd greater than that of Nh, where Nd is number density of donor atoms. For p-type semiconductor, Na is nearly equal to Nh greater than that of Ne, where Na is number density of acceptor atoms. Electrical conductivity of a semiconductor. The total current passing through the conductor is given by I equal to Ea Ne Ve plus Nh into Vh, where Ne represents electron density, Nh represents hole density, Ve electron drift velocity, Vh hole drift velocity. If electron mobility and hole mobility are given, mu E represents electron mobility, mu H represents hole mobility. The conductivity in the semiconductor is given by sigma equal to E times Ne into mu E plus Nh into mu H. The reciprocal of resistivity is called conductivity, or the reciprocal of conductivity is called resistivity. Rho equal to 1 by sigma. So rho equal to 1 by E into Ne mu E plus Nh mu H. The conductivity of an intrinsic semiconductor increases exponentially with temperature. So that expression is given. First problem here. In a semiconductor, the concentration of electrons is 8 into 10 power 14 per centimeter cube. That of holes is 5 into 10 power 12 per centimeter cube. The semiconductor is. In the problem, it is clear that the concentration of electrons is more than that of concentration of holes. So this is a n-type semiconductor. So the correct option is B. Second problem. Let Np and Ne be the number of holes and conduction electrons respectively in a semiconductor. Then already we discussed that in the case of intrinsic semiconductors, the number of electrons present in conduction band is exactly equal to number of holes in valence band. So in the case of intrinsic semiconductor, Np equal to Ne, so option C is correct. Next problem, third one. In extrinsic P and N-type semiconductor materials, the ratio of the impurity atoms to the pure semiconductor atoms is about. So in the explanation, and I told you that the impurities are added to a pure semiconductor in the ratio of about 1 in 10 power 7 atoms. So here we want the ratio of impurity atoms to the pure semiconductor. So 1 divided by 10 power 7, which is equal to 10 power minus 7, the correct answer is D. Next, fourth one. A p-type semiconductor has an acceptor density of 10 power 20 atoms per meter cube and intrinsic concentration of 2.5 into 10 power 19 meter power minus 3 atoms per meter cube at 300 Kelvin. The electron concentration in this type is. So in the case of p-type semiconductor, Na is nearly equal to Np. Na is given as 10 power 20 atoms per meter cube and intrinsic concentration Ni is given as 2.5 into 10 power 19 atoms per meter cube. So by using the formula Ne into Np equal to Ni square, we can get Ne value 6.25 into 10 power 18. Students, do that simple problem only. Next one, fifth one. The intrinsic carrier density is 1.5 into 10 power 16 meter power minus 3. If the mobility of electron and hole are 0.13 and 0.05 meter square volt inverse second inverse, calculate the conductivity. Ni is given as 1.5 into 10 power 16, mu E is 0.13 and mu H 0.05. We know that conductivity is Ni into E, mu E plus mu H. So sigma equal to Ni 1.5 into 10 power 16, charge of electron 1.6 into 10 power minus 19 times 0.13 plus 0.05. Simplify, students. By simplification you get sigma as 4.32 into 10 power minus 4 ohm inverse meter inverse. The SI unit of conductivity is ohm inverse meter inverse. Next, sixth one. The intrinsic carrier density at room temperature in germanium is 2.37 into 10 power 19 per meter cube. Electron and hole mobilities are given 0.38 and 0.18 meter square volt inverse second inverse. Calculate the resistivity. In the previous problem, we calculated conductivity. In this problem, we have to calculate the resistivity. Ni is given as 2.37 into 10 power 19 per meter cube. Mu E is given as 0.38, mu H 0.18. Conductivity sigma Ne into mu E plus mu H. Substitute the values. We get sigma equal to 2.12 ohm inverse meter inverse. The reciprocal of conductivity is called as resistivity, denoted by rho. Rho equal to 1 by sigma. Therefore, rho equal to 1 by 2.12. Resistivity, by calculating, we get 0.47 ohm meter. Seventh problem. Students, I am giving one problem for each model for our understanding. Do that and practice 3 or 4 times. If you have any doubts, and you call me. In a p-type germanium, Ni is 2.1 into 10 power 19 meter power minus 3. Density of boron is 4.5 into 10 power 23 atoms per meter cube. The electron and hole mobility are 0.4 and 0.2 respectively. What is its conductivity before and after addition of boron atoms? In this problem, we have to calculate the conductivity before the adding of impurity and after adding the impurities. In the theory part, we discussed that by adding impurities to a pure semiconductor, conductivity increases. In this problem, you can understand that. Yeah, Ni is given as 2.1 into 10 power 19 per meter cube, mu E 0.4, mu H 0.2. First part, conductivity before the addition of boron atoms, sigma equal to Ne into mu E plus mu H, 2.1 into 10 power 19, 1.6 into 10 power minus 19 into 0.4 plus 0.2, and simplify that, you will get 2.016 ohm inverse meter inverse. That is the conductivity in this case before addition of impurity. Yeah, next, conductivity after the addition of boron atoms, sigma equal to P, that means Np into E into mu H, 4.5 into 10 power 23 times 1.6 into 10 power minus 19 into 0.2. Charge of electron or proton 1.6 into 10 power minus 19 and 14,400 ohm inverse meter inverse. So before the adding of impurity, sigma is 2.016. After addition of impurity, we get 14,400. Conductivity increases. Next problem, 8th one. In an n-type semiconductor, the concentration of electrons is 2 into 10 power 22 per meter cube. Electrical conductivity is 112 ohm inverse meter inverse. Calculate the mobility of electrons. Conductivity sigma 112 ohm inverse meter inverse. Carrier concentration Ni 2 into 10 power 22 atoms per meter cube. Students, I have given another new parameter, Hall coefficient, that is not in our syllabus. In higher studies you have that, but that is a small thing, so that's why I have given Hall coefficient RH equal to 1 by Ne. So substituting N and E values, you get Hall coefficient as 3.125 into 10 power minus 4 Coulomb inverse meter power minus 3. Mobility means mu equal to sigma into 1 by Ne, or conductivity equal to Ne into mu. From that formula, mu equal to sigma into RH, 112 into 3.125 into 10 power minus 4, and by simplifying, mobility mu equal to 0.035 meter square volt inverse second inverse. Find the resistance of an intrinsic germanium rod 1 millimeter long, 1 millimeter wide, 1 millimeter thick at 300 Kelvin. The intrinsic carrier density 2.5 into 10 power 19 per meter cube at 300 Kelvin. Mobility of electron and hole are 0.39 and 0.19. This is the another model, students. Length of the rod is given as 1 mm, 10 power minus 3 meter, breadth 1 mm, thickness 1 mm. Intrinsic carrier concentration and mobility of electrons and holes are given. And first of all, I calculate the conductivity, sigma equal to Ne into mu E plus mu H. Substituting the values, sigma equal to 2.32 ohm inverse meter inverse. In lower standards, you know that R equal to rho L by A, where rho is specific resistance or resistivity. So in the place of rho, if we substitute 1 by sigma, resistance of the rod R is L by sigma A, where L is length of the rod, A is area of cross section of the rod. Area of cross section is breadth into thickness. And substitute the values, 10 power minus 3 by 2.32 into 10 power minus 3 into 10 power minus 3. We get the resistance of the rod as 431 ohms. Tenth one, the intrinsic carrier density of a semiconductor is 2.1 into 10 power 19 atoms per meter cube. Electron and hole mobilities are 0.4 and 0.2 respectively. Calculate the conductivity. Already we completed this model. Ni, mu E, mu H are given. Conductivity sigma equal to Ne into mu E plus mu H. 2.1 into 10 power 19, 1.6 into 10 power minus 19 into 0.4 plus 0.2. Conductivity 2.016 ohm inverse meter inverse. Eleventh problem. The electron mobility and hole mobility in silicon are 0.135 and 0.048 respectively. If the carrier concentration is 1.5 into 10 power 16 per meter cube, calculate the resistivity of silicon at room temperature. In this problem, carrier concentration, mobility of electron and holes are given. Conductivity sigma is Ne into mu E plus mu H. Substituting, you get sigma as 0.439 into 10 power minus 3 ohm inverse meter inverse. The reciprocal of conductivity is called resistivity. Rho equal to 1 by sigma. Rho value 2.27 ohm meter. Twelfth one, mobility of electrons and holes in a sample of intrinsic semiconductors at room temperature are 0.36 and 0.17 respectively. If both electrons and hole densities in semiconductor equals 2.5 into 10 power 19 meter cube per meter cube, then conductivity of semiconducting material. sigma equal to Ne into mu E plus mu H. Yeah, 1.6 into 10 power minus 19 into 2.5 into 10 power 19 per meter cube into 0.36 plus 0.17. Simplifying, we get 2.12 ohm inverse meter inverse. Ohm inverse is nothing but Siemens per meter. In a pure silicon crystal at 300 K, 10 power 21 atoms of phosphorus are added per cubic meter. New hole concentration is. Here Ni is given 10 power 16 per meter cube, and phosphorus atoms 10 power 21 atoms per cubic meter. Hole concentration we have to calculate. Mass action law, Ni square equal to Ne into Nh. Here donor concentration is nearly equal to Ne. So Nh equal to Ni square by Ne. 10 power 16 whole square by 10 power 21. So whole concentration in this case is 10 power 11 per meter cube.